So this is, oh boy. Okay. All right, so this is what we were starting last time. Here, remember, what we're doing is we're in section P5, okay? And we're looking at rational expressions. That is what we're looking at, rational expressions, okay? Yeah, we'll go through what they are again. I'm also going to show you how we can multiply and how we can divide them, okay? What I'm also going to show you is how to add and subtract them as well. So again, we're going to see what a rational expression is. We're going to see how one can multiply and how we can divide them. We're also going to see how to add and how we can subtract them. We're also going to see that, okay? All right, so what is a rational expression? Well, by definition, a rational expression, okay, that's just a quotient of two polynomials. You know, it's kind of like when you have integers, right? You form a quotient of them, you get a rational number. It's the same idea, except instead of integers, we have polynomials. A rational expression, okay, it's a quotient, right, of this form. And this is where, again, P and Q are two polynomials, okay? So that's what a rational expression is. It's essentially, it's a fraction of polynomials. You know, here are just some examples. You can see. So also, any polynomial is itself a rational expression because you can divide by 1. You know, if you divide by 1, you're not really changing anything, okay? So if you divide by 1, that is, you're not really, you know, changing anything essentially. So any polynomial is itself a rational expression. Okay, so this is what we get here. All right. Now, we did talk about domain, you know, like domain of domain of functions, that is, we have talked about. There is the concept of a domain of a rational expression, and it's by definition, it's all the numbers except those where the denominator is 0. It's not by definition, excuse me. But it is, though, where it's the collection of all numbers that except those that make the denominator 0. In other words, if this was your rational expression, okay, the domain would be all numbers x such that q of x is not 0. You know, because you can never divide by 0. And that's why. But now, how do you actually find that? Well, what you do is you solve this equation. You form this equation where the denominator equals 0, okay? And then, you know, you solve it, and the domain is all numbers except those solutions. So it's everything else, basically. Okay, so that's what we get here, okay? Let's do an example of that. For instance, let's find the domain of this rational expression. So we have the denominator, which is this, right? I mean, here it's nice. It's already factored for us, okay, as you can see. And now what we're going to do is we're going to set this product equal to 0. And remember, the way you would solve this is you set each factor equal to 0, right? You set each factor equal to 0. So we get x equals 0, x minus 2 equals 0, x plus 3 equals 0, right? And we solve each equation. I mean, the first one is easy. You just get 0 as the solution. For the second one and third one, you solve for x. That's what we're doing here. We have x minus 2 equal to 0. So we add 2 to both sides, right? Because you want to get x all alone. We get x on the left equals 2. For this one, we have x plus 3 equal to 0, right? And then, you know, we subtract 3 from both sides. We get x equals minus 3. Again, we want to get x all alone on the left side, okay? So the solutions then to this equation are 0, 2, and -3. Okay, the domain is everything else. So the domain is all numbers except 0, 2, and -3. So the domain then is everything else. Are there any questions on that? Okay. Here's another example, right? We have this rational expression. The denominator, is a quadratic, okay? So you want to know when this equation holds. I mean, you could try factoring it, but personally, mostly because the coefficient of x squared is greater than 1, I personally would just dive right in to the quadratic formula. You know, you have a is 3, b is 5, c is 11, right? So what we get here is x equals -b plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. That's what we get here. Well, that's the quadratic formula. So using this, we get -5 plus or minus the square root of 5 squared minus 4 times 3 times 11 over 2 times 3. You know, we get this. And of course, from here, as you can see, what we end up getting is this here. -5 plus or minus the square root of -1 over 7 over 6. Now, since we have the square root of a negative, right? You know, that's not a real number. So because of that, the quadratic equation is telling us there are no solutions to this equation. Again, you can't take the square root of a negative number here, right? So this has no solutions, which means this is never 0. The denominator is never 0. Hence, the domain is everything, all real numbers. So written as an interval, of course, we get this. So the domain, though, is all real numbers. Again, that's because the denominator is never 0. You know, we're not dealing with complex numbers here. We're only looking at real numbers. All right. Any questions on that? Okay. Now, with fractions, as you already know, you could actually write them in lowest terms. You know, we can do that. Well, you could do the same thing with rational expressions. Namely, we simplify them. So a rational expression is said to be simplified if the numerator and denominator have no common factors except 1 and -1. Excuse me. I mean, 1 and -1, those are always going to be factors, common factors. You can't get around that. So we say it's simplified if those are the only two. Now, the factor theorem does help us here, okay? The factor theorem, remember, if you have a polynomial p of x and a real number a, for any polynomial p of x, and real number a, x minus a is a factor of p of x, that polynomial, exactly when p of a is 0. You know, that's what we saw from the factor theorem. Okay? You know, we saw that already. All right. Now, to simplify, though, a rational expression, what we have to do is factor the numerator and denominator. Now, what's nice is sometimes you don't always have to do that. By the factor theorem, you may only have to factor one or the other. I mean, you could always factor both, but you may not have to, okay? Because you just want to check if they have any factors in common. And if they do, you cancel those. Okay? I mean, we'll do some examples of that, but basically it boils down to finding the common factors and canceling them. You know, you could factor and then cancel. But again, the factor theorem can help you here. For example, let's simplify this first expression here. And I just wrote this also. Sometimes you're going to see with rational expressions what some people will do, or some sources, I think our textbook does it, they'll have something like x not equal to a number, a, where a is just some number. They will write that, and basically what they're assuming is they're working in the domain of the rational expression. In other words, they're basically saying x is not this number, a, that a represents, because that's where the denominator is 0. That's all. I mean, you won't always see that, but you might see that in the textbook. All right. So here we're basically going to assume in the background that x is not -2, right? Because if x were -2, the denominator would be 0. And that's a no-no. Okay. Now what's nice about this one is the denominator is already factored. The numerator, let's see if we can factor that. Well, notice that we have x squared. That's the smallest power of x, right? So what do? Let's factor it out. For x squared, let's factor it out, right? Just like when we factored out GCFs. So we have x squared in front. We divide to see what's left over. When you divide into each term, like so. You get x squared times x plus 2. See? X squared times x plus 2. Right? Because that's what we get here. Because when you divide, remember, you subtract exponents. Now, if we have that in the numerators, you can see what's going to happen is there's cancellation, right? You know, we just factored the numerator, so we got this. But the x plus 2's are going to cancel, as you can see. And we get x squared. We get x squared. So we simplified this and got x squared. And again, we were assuming x is not -2. Okay, because again, if it were, the denominator would be 0, and that wouldn't make sense. Are there any questions about this?